Hey guys, welcome to Chapter 7, Part 3. So we were just talking about how Bohr has proposed another change to the atomic model. So based on the ideas that came out of the photoelectric effect and line spectrums that are specific to each atom, Bohr took these ideas and used them as evidence to propose another change, which would be the energy levels that we find around an atom. So the logic flow that you should kind of be able to explain is how like specific colors in the line spectrum relate to very specific energies, like energy of a photon, and how that leads to very specific distances between the electron and the neutron. So colors can be described in wavelength or also frequency. Energy is going to be big E, energy of a photon, and then the distances, this pertains to the model of the electron. So as you're reading through Chapter 7, all of these come with equations, and the equations are what Bohr used. Bohr was a mathematician. He was like a physicist mathematician. So he used these equations. He wrote these equations to describe the model. And so what you should be able to do as we are getting into the equations, this is the next thing we're going to look at. What you should be able to do is kind of pull these equations apart and explain what each of the parts mean or represent and how they relate to the evidence of the line spectrum, pretty much, and the model that it's describing. Okay, so we're going to go through these equations. And the important thing is not so much that you can calculate an answer. I know we look at an equation and we start looking at the variables and we just want to plug numbers in and punch it into our calculator and check out an answer. But that's not necessarily what we want you to do. The idea really is that you can explain what these equations represent and how they tie evidence to the model, how the evidence is used to support the model. So when you're looking at the AP test, that's kind of the questions that we see coming off the AP test also. We see questions that ask you, not to calculate a specific amount of energy or a specific energy level. What we rather see is you being able to explain through the equations, is energy being absorbed or is energy being released? What is this describing? What kind of line would this be describing? So the answer is not the important part. It's being able to just explain what these equations are describing. Okay, so hopefully that takes a little bit of pressure off of you as you're looking at these equations in the book, and also helps you to orient, like, yes, our textbook is going to ask you to do some of these equations, but it's not necessarily the answer that's important. It's that you are able to functionally deal with these equations and kind of explain what the answer means. Okay, so let's kind of talk through some of these equations that you're going to see. Remember, these were developed by Bohr and his team to describe the atom of hydrogen, and he's basing all of these off of the line spectrum of hydrogen. Okay, so here's one of the first ones right here. Okay, so E here is the energy of a photon. And remember, those photons can be absorbed by electrons, and then the electron will move to another energy level, or they can be emitted by the electron as the electron moves down. So this energy can kind of go both ways. R here is the Rydberg constant. It's just a number that makes the equation work. right? So when you're trying to come up with a relationship between two things, and you want a mathematical relationship so that you can plug in one variable and predict the other variable, oftentimes you're going to need some factor in there that just makes the equation work mathematically, right, inside your calculator. And so that's what R is. It's a number. It doesn't change. It just makes the equation work. It's on your reference sheet. If you really need it, you can just go look it up. N, on that side, N is going to be your energy level. So this is an equation that relates your distance. So the distance between the nucleus and the electron, that would be N. What N are you on? What energy level is your electron on? And because your electron is on that energy level, what energy has it absorbed to get there, or has it emitted to get there? Kind of an idea. So N starts, if you have your nucleus down here and you start having your energy levels circling around, N is going to start small and get bigger and bigger as you move out. And it's going to, as the electron moves away from the nucleus, N is going to approach infinity, is kind of the idea. Okay, now, this equation down here, we see some of the same factors. So again, C is going to be a constant, just makes the equation work. You can go look it up. It's probably on your reference sheet. This, on this side, this is nu. So this is the frequency of your photon, or of the light. And then notice that N, again, is going to represent which energy level are you on. And it's always in comparison to 2. So it's always going to be in comparison to the second energy level, right? So if you have your nucleus, and this is 1, 2, 3, 4. Okay, so the electron, the idea here is that the electron is changing levels because we have an N and then we have a second N. And the second N is 2 here. It's always being compared to 2. So you're going from 3 to 2, or from 4 to 2, or maybe from 1 to 2, right? It's always going to be a change from an energy level to the second energy level. And what this gives is called the Balmer series. It is one of the hydrogen line spectrum. And the Balmer series specifically is the visible light spectrum. So when you look at a line spectrum and you see all those little lines, we can actually flip up here to the line spectrum. Okay, here, when we see these visible light lines down here, these are the Balmer series. Any emission line that hydrogen will give off that is in the visible light series, visible light spectrum, is going to be part of that Balmer series. Okay, so that's why it's specifically to the second energy level with respect to the second energy level, because if an electron is always falling to the second energy level, it's going to give off light within the visible range. If it's falling, let's say, to the first energy level, it's going to also give off a line spectrum, but that line spectrum is not going to fall within the visible light spectrum. It's going to probably fall outside of that. Okay, so I think that kind of describes it. So if we compare these two equations, really what you see here in the first equation is energy that is contained when the electron is at a specific energy level, N. And in the second one, it's the energy that is released when the electron falls from a higher energy level to the second energy level. Okay, and that's why it gives off nu, or a specific frequency. It's going to lead you to that very specific frequency that you can see in the hydrogen line spectrum. Okay, so Bohr's quantum model, therefore, what he proposed was energy levels exist, but they exist as circular orbits. Oops. And that orbit pertains to an allowable energy level, and any kind of fraction in between those allowable energy levels is not allowable. The electron can't exist there, which is why we don't see those wavelengths of light. Those wavelengths of light in our line spectrum are just going to appear as black, right? There's no wavelength that we can see coming out of there in the line spectrum. And again, he also proposed, like, if electrons jump, that they can jump between energy levels. They can move from 1 to 2. If they absorb energy, they're going to go to a higher energy state, also known as an excited state. If they emit light or energy, they're going to fall to a lower energy state, and the lowest energy state possible for any given electron is going to be called the ground state. So lower energy states are closer to the nucleus, think like lower potential energy. Higher energy states are farther from the nucleus, think like higher potential energy. Okay, so if we're looking at equations here, we saw the Balmer series equations. We talked about this one. Here is allowable energy. So where are those energy levels? We can figure that out with the second one. If we're talking about a change in energy, so if the electron has undergone a change in energy, changes in anything are going to be calculated final minus initial. So see this triangle here. This triangle means change in energy. And we calculate the change final minus initial. So if you go to the store, or if you go to work and you work for 10 hours and you earn money there, and we want to know the change in your bank account, we would go your final amount that you had minus the initial amount you had when you walked into work, right? We wouldn't calculate it the opposite way. So that change in energy is going to be H nu, which we also talked about before. And so this is the equation that really relates the specific color to the specific energy. So here's that relationship we were talking about. You can follow these equations now. We talked about how, like, a specific color will lead you to a very specific energy. And that equation is going to be E equals H nu. From a specific color, we can calculate a specific energy. And then also, that specific energy is going to lead us to a specific distance away from the nucleus. And so that is this second equation. Okay, specific energy will give you a specific distance, a specific location for that electron with respect to the nucleus. So you can explain this relationship using the math, which is where we want to get to. Okay, so if you take these equations, you can kind of plug these equations into each other to verify different things. So you just take the equations and manipulate that. Zumdahl loves to derive equations. They love to derive equations because Zumdahl believes strongly, I mean, I don't know the guy, but from reading his textbook for so many years, I gather that Zumdahl believes strongly in not memorizing stuff. He doesn't just want you to memorize it and not understand the reason behind it. And so Zumdahl shows you how to, like, plug equations into each other and explain stuff. If you look at other textbooks are going to approach it differently, and they'll just tell you, like, this is how it is. And it's a much simpler view. You don't have to process as much information at the same time, but you also don't ever get that explanation of, and here's why. So that's why we went with the Zumdahl book, because it kind of gives you the best of both worlds if you want it. And one of those examples is kind of this section that I have here. If you take, so we're taking this equation here that relates a specific color to specific energy and just manipulating it so you're solving for frequency, right? And then you plug in Bohr's allowable energy, which is here. If you plug that equation in, so you get basically H and then E final minus E initial, also known as H negative R 1 over N squared minus negative R 1 over N squared. And we make this one final and this one, N squared, not N2, initial here. Okay, notice that here's your constants, H's and R's can be combined into one constant. Let's call it C. And then you have 1 over N squared final minus 1 over N squared initial. And what does this equation look like? Shauna, it looks like the Balmer series, right? Especially if our N final is energy level number 2. Okay, so again, we're just kind of using these equations to verify the model, which is, this is what Bohr did to build his model. He took these equations and he built his model off of them. All right. Just one side note here. If you ever calculate a negative frequency, it's not any like supernatural, strange, weird concoction of like that turns into a black hole or something like that. It just, what the negative and positive mean is the direction of energy relative to the system. So is energy coming into the system? Is it being absorbed by the electron, or is energy leaving the system? It's being kicked out of the system, right? It's being emitted from the system. So that's all the negatives and positives mean if you get a negative frequency. It's just talking about the direction. Is it being absorbed or emitted? All right, so you can take this and calculate the wavelength of light, and we can do this together. We'll try that together. So Bohr made this, kind of took all of these revolutionary ideas from all of these really fantastic minds of the time, like Balmer and Einstein, and he built this revolutionary chemistry and physics changing model, right? But there was one problem with Bohr's really awesome model. It only worked for hydrogen. So it worked beautifully for hydrogen. It perfectly described the line series that came out of hydrogen. It perfectly predicted series other than the Balmer series, the ones that were in the ultraviolet range, the one that were in the infrared range. Years later, when we finally had the technology to detect ultraviolet light or infrared light, they actually found the line spectrums in those regions for hydrogen, and they perfectly matched Bohr's model. It was amazing, but it didn't work for helium or lithium or beryllium or boron. It just didn't work for these. And so again, we take this model that beautifully describes what we're seeing and predicts things that we can't detect yet, but they were able to in the future. And we don't toss the whole model out, right? We change the model. So the model had to be changed so that it encompassed more than just hydrogen. And this is where that light electron crossover really comes into play. You know, the photoelectric effect had a little bit of this, like, is it a wave? Is it a particle? You know, light, we think, might have and then a little bit of the nature of both. Light definitely has wave-like nature, but it also might have particle-like nature. Maybe it exists in bundles of energies, quantums of energies, right? Well, so fast forward that to this issue of hydrogen versus all the other elements. And the question you want to ask yourself is, what's the difference? What's the difference between hydrogen and all the other elements? And one of the differences is there's more than one electron, right? So all of a sudden you have these systems. A system of one electron behaves very predictably, but a system of two electrons, all of a sudden you have this interaction that we can't explain, right? And so the theory gets flipped. Maybe a wave is both a wave and a particle. It has this dual nature. Well, maybe particles also have that dual nature. We think of particles, what's matter? It has mass, it takes up space, right? Well, maybe matter has not only these particle-like characteristics, but they also have some wave-like characteristics that we don't necessarily detect unless you get into specific situations. Okay, and this is kind of what gets us from Bohr's model into the current model of the atom, which is called the quantum mechanical model. Okay, so in order to talk about electrons and this wave-like character they may or may not possess, let's talk about what wave-like character is, right? We've talked about characteristics of a wave. Has a crest, has a trough, has an origin, has an amplitude, has a wavelength, has a frequency, has a speed, right? But some other things that light does is light interacts with each other. So if we take our waves and we talk about that interference that we were talking about earlier today, right? If we take waves and we get them to interact with each other. Think about dropping pebbles in a pond. We drop a pebble here, it creates a series of waves. We drop a pebble here, it creates a series of waves. And in between them, we get a pattern, right? And this happens because of wave interference. So when we have waves and they line up, so their crests and their troughs happen at the same place, what happens is these waves are additive. They actually build on each other. So we get the amplitude of one and we get the amplitude of another, and they actually build upon each other to create this super high and this super low. This is called constructive interference, where waves crests, they line up and they add. And this, we also have a phenomenon that's similar. It's called destructive interference, right? So we have the waves, same waves, but their crests and their troughs actually don't line up. Their crest lines up with the trough, and the trough lines up with the wave. So what happens is the crest of one and the trough of the other are actually going to subtract from one another. And what you get is kind of a muted wave. Oops, I didn't do that very good, but here. Okay, so when their crests and their troughs line up, you get waves that really subtract each other. So you get this constructive interference where waves build. You get this destructive interference where waves subtract. And we can imagine this pretty easily with water, right? As waves are rolling into the beach, when one wave catches another wave, it gets into this, it just builds this giant wave. Or as one wave is rolling in and one wave is rolling out, if they just so happen to meet at a specific point before they keep going, the wave like flatlines for a second before you see the waves appear on the other side and then keep moving. So constructive interference where they get bigger before they move on. Destructive interference, where they get smaller before they move on. So light, any wave does this. Light waves do this. You get bright spots and dark spots. Water waves do this. You get big waves and small waves. Sound waves will do this, where you get loud spots in an auditorium and you get dead spots in an auditorium. So if waves do this, could electrons do this? So before we talk about all of this stuff happening with the electrons, I want to show you some of these patterns that happen. You know, we can imagine what happens when waves interact, like dropping pebbles in a pond, but I want to show you the patterns that happen. So the first thing I want to show you is, this is an Acura commercial, and it talks about noise canceling technology in their engine. And so I want you to think while you watch this, would this be constructive interference of sound waves, or would it be destructive interference of sound waves?
Most automobiles use only insulation to reduce noise. But we take a different approach. We use microphones to detect unwanted engine sounds, then transmit opposing frequencies to eliminate them. Literally fighting sound with sound. Active sound control, available in the Acura TSX. You'll find in an Acura.
Okay. So hopefully you saw that and realized that is going to be destructive interference. So they're using destructive interference of sound waves to cancel out the noise of the engines to their advantage. So you can see that this pattern happens with all kinds of waves, including sound waves. So here's another example. So this is salt sitting on top of a speaker, and you can hear the speaker is trying to just play one single note, get to a specific frequency. And when it hits that frequency, the waves that are traveling over the surface of this are interacting with each other, and they're making a pattern. And so you can see as they're changing the tone up. I'm going to turn this volume down just a little bit. So as the tone gets higher and higher, the waves are getting smaller and smaller. And the interaction patterns of those smaller waves are getting more and more complicated. I'm going to turn the sound down because it's a little painful. So when we're talking about interference patterns of waves, this is what we're talking about. Constructive interference is going to make a big wave that's going to push the salt away. Destructive interference is going to make this like canceled out wave where the salt can settle, and it forms an interference pattern. Oh, that pitch is so nice. It's still there, just really high. Okay, there, they finally turned the sound off. So again, this is just such a great example, such a visual example of interference patterns. When waves interfere, they create patterns. You can see here is an interference pattern of light waves. So the constructive interference would result in bright light. Destructive interference would result in no light being there. Okay, so We're going to talk about interference patterns with electrons. So again, if light can have this dual nature of wave characteristics and particle-like characteristics, then maybe particles also have this dual nature. All right, so as all of these theories are being developed, there's a whole bunch of kind of scientists speaking in to this developing theory, and Heisenberg was another one of these scientists. So Heisenberg was a classic physicist, and so he is used to dealing with, like, think of a cannonball being shot across a field, right? When physicists were studying, motion and velocity and momentum and friction and trajectory and all of these things, basically what they wanted to know with all these objects was, where is the object and where is it going? So Heisenberg was trying to apply these principles to an electron. Where is the electron and where is it going? And what he started looking into was the uncertainty of it. What is the uncertainty of an electron? An electron is so very small and it's moving at such an incredibly high speed. How well can we know the location of that electron within a degree of certainty? I mean, do we know if the electron is in a 1 nanometer space, or is it in a 3 nanometer space that we can say it's definitely within this 3 nanometer space somewhere? We just can't say it's in this 1 nanometer. Or can we know it within, a meter space? We definitely know the electron's here somewhere. We just can't pinpoint where it is. So Heisenberg started looking into the statistics and the uncertainty of it all. And what he developed was this equation right here, which is the Heisenberg uncertainty principle. And so this delta X is uncertainty of the location of an electron, and this delta P is uncertainty of the momentum. Momentum is mass times velocity. So basically, the X would be how well do we know where the electron is, and the P would be how well do you know where the electron is going. And what Heisenberg found out was, if we take, a relatively reasonable degree of uncertainty, let's say 1% uncertainty, and we plug that into the equation, if you take 1% of an electron's mass here, and you take 1% of its velocity here, to a 1 degree uncertainty, you're just looking at the uncertainty of the momentum itself, and it comes out to be this like astronomical amount. And so what Heisenberg's equation and statistics kind of concluded was, it's impossible to know both the location and the momentum of the electron to a reasonable degree of certainty. If you know one of them within 1% of uncertainty, the other one is just enormous. You can't know them both at the same time. And so this was another huge shift for the electron. All of the physicists and chemists that were studying the structure of the atom basically made a big shift at this point in time. Instead of talking about an electron as if it's a cannonball that we can hold and set down and it'll stay there and we can study it, we need to start looking at the electron in terms of probability. What's the probability it's in this area? What's the probability it's going to avoid this other area? So instead of talking about like specific locations, there was this shift towards talking about probability. So all of this is in the quantum mechanical model. We're going from Bohr's model, where Bohr said, all right, so we have electrons, we have a nucleus, we have electrons around the nucleus. They're a very specific distance away from the nucleus, and it's like they're running around a little track. So Bohr was treating the electron as a classic physicist would treat the electron. And then there were all these shifts that were made. We really can't talk about the location and direction of an electron with uncertainty. So instead of talking about it as if it's, here in this exact position at this exact time, let's talk about, okay, over the course of an hour, an electron, if this is the nucleus, the electron could be here or here or here or here. If we just start taking a snapshot, okay, this second it's here and this second it's here, and we just take all these snapshots of the electron every second and we compile all these snapshots, what we get is a probability area. Okay, well, we see that most of the time the electron is existing close to the nucleus. Sometimes it moves out of that region, but we can draw a circle around 90% of where the electron spends its time. So we can expect that 90% of the time we're going to find the electron within that boundary. And so we'll call that energy level 1. It's not a track, it's not a racetrack for the electron. It's this region where we will find the electron 90% of the time. This is the next shift to the model. And so what we're seeing is this development of the next model called the quantum mechanical model. And this is the model we use today. Another thing that was used to describe the electron and where it is Schrodinger's equation. So this right here is Schrodinger's equation. It's kind of a beast. My favorite picture of Schrodinger's equation is, I think I have it here. Yes, this guy. I love this guy. Look how happy he is. He's so excited and thrilled about Schrodinger's equation. I just cherish the expression that's on his face. So Schrodinger's equation is an equation with lots of variables. You can see across here, look at how many different variables there are in here. And so what Schrodinger's equation does is you kind of plug in this variety of parameters, and what you get out is called a wave function. That's this symbol. So that symbol in the equation is kind of the answer that you get out of this equation. And the wave function is a probability map. It's a map of where you would find the probability. So it's not just a number. You're not going to plug it in and just get out 4 on your calculator. What you would get out is a picture. So I don't know if you played with graphing calculators in your math class a whole lot, but there is a math class. I'm not sure if it's Algebra 2 or if it's pre-calc, but basically what you do is you spend a little time figuring out the graphing on your graphing calculator, and you can plug in a series of equations and you can create a picture. And a simple picture would be like a sphere. You plug in a variety of equations, you get a couple of these lines that are drawn, and you create a sphere. And if you get really good, you can draw simple pictures like Winnie the Pooh or Calvin and Hobbes. You could design some lines that when you hit enter, what it's going to do is draw you a picture on your graphing calculator. And that's kind of what a wave function is. The answer to a wave function is a picture, just like a picture on your graphing calculator would be. And what the picture is it's a picture of where the electron is likely to spend its time. The areas of probability where the electron is most probable to spend its time. This is what we call a wave function. And so we're moving away from electron tracks, and we're moving into three-dimensional areas of probability where we are likely to find the electron. And this is what we need to be able to describe in order to describe where electrons live around an atom. Okay, that's what we just talked about. Okay, so this is an example of one. This would be a Schrodinger's equation answer. This would be one of the wave function. So it draws a picture. And again, we can think of this as like if we take a snapshot of the electron every second, and then we layer all of those pictures on each other, we might find something like this. And we can draw a boundary around 90% of the probability for our electron. And that shape that we get out of here is our energy level. So this is actually one of the energy levels for the electron. What shape would you say that is? And remember, it's in 3 dimensions. So it's going to be a sphere. So one of the energy levels for the electron looks like a sphere. So this is what we need to move into. We need a way, if we're going to talk about the quantum mechanical model of the atom and the structure of the electrons around the atom, we need to be able to have a system or a way to talk about these areas of probability. And so that's where we're going next. We need to be able to talk about these areas of probability. So let me run you through some of these quickly. Here are some examples. So the very simple ones you can see are a sphere, but they get more complicated and more complicated and more complicated. And that is, think back to salt on a speaker. The more electrons you get in here, it'd be like the more waves you get interacting. And as you get more waves interacting or more electrons interacting with each other, your picture is going to be more and more and more complicated. Also, it's easiest to think of the electrons in terms of like forcing each other in or out of certain areas. So the waves, they'll build or they'll reduce each other so that you get really big waves or really small waves or no waves at all in certain areas. And that's kind of what draws your picture. With electrons, it's more like the electrons force each other into certain areas or out of certain areas, right? You're dealing with the force of attraction between the electron and the nucleus, but also the force of repulsion between an electron and another electron. So all of these forces are going to kind of push each other in and out of certain areas, and you get these areas of probability that are our energy levels. So there's 4 things you need to be able to describe about each energy level. Okay, we're going to use kind of a code to talk about these things: N, L, M sub L, and M sub S. When we talk about these codes, it describes specific areas where the electron lives. And so you can kind of think of it like a street address. If we live at 1500 Northwest 15th Avenue, McMinnville, Oregon. Okay, so each part of our address kind of zeroes us in a little farther on our location. First I tell you the state I live in. So that's pretty big. I live in Oregon. Okay, McMinnville. So that zeroes me into a smaller area. Okay, I'm on 15th Avenue. And so that's going to be a specific street within Oregon or within McMinnville. And then my address here, 1500, gets me a specific house on that street. So in the same way, all of these quantities that are describing the orbitals or where the energy levels where the electrons live, it's going to kind of get you into a smaller and smaller and smaller area until we have all 4 parts of our description. And if you have all 4 parts of your description, you're describing where one electron exactly lives. So let me just tell you what all four of these are, and then we can kind of go into depth in all four of these in class today. So N is going to be your principal quantum number. It's going to describe the size of the orbital that you're talking about. And a term, if you just have the N where the electron lives, you would call that the energy level. L is going to be the angular momentum quantum number. L is going to describe the shape that you are, that the electron, the shape of the area of probability where the electron lives. M is going to be the magnetic quantum number. This is going to describe the orientation of your shape. So is your shape oriented on the x-axis or the y-axis or the z-axis, right? If you have the N, the L, and the M sub L, you're talking about an orbital. If you just have the N and L, you're only talking about the suborbital. And then M sub S is going to describe actually less about the shape of the orbital itself, and it's actually going to describe the electron itself. So this one is called the magnetic spin quantum number, and the thing that it describes is about the electron. Is the electron, which direction is the electron spinning? So direction of spin of one electron. And if we have all four of these, N, L, M sub L, and M sub S for a specific electron, we are describing only one specific electron that is living around our atom. All right, and we will dive into these quantum numbers and go through a myriad of examples to kind of wrap your brain around how to deal with them and what kind of questions you'll be asked and why they're useful. We'll do that in class today.